With today's powerful computers and advanced computational methods, engineers and scientists are taking on the great challenges of our time. Renewable energy, new medicines and healthcare technology, clean air and water, smart transportation systems, and weather and climate forecasting. For over 25 years, MATLAB has been the computational engine for discovery and innovation. MATLAB is a high-level language for easy expression of engineering and scientific ideas. A language taught at universities around the world to train the next generation of engineers. MATLAB has a vast algorithm library based on a strong foundation of mathematics that embodies the latest techniques in linear algebra, signal and image processing, communications, control systems, and many other domains. Today, over 1 million engineers and scientists use MATLAB as a common language for sharing ideas and collaborating across disciplines. They use it to model energy consumption to build smart power grids, analyze weather data to visualize the track and intensity of a hurricane, develop algorithms to optimize hybrid vehicles, and run millions of simulations to pinpoint optimal dosing for antibiotics. With MATLAB, engineers and scientists accomplish in minutes or hours what would take days, weeks, or months with conventional programming languages. They speed up their work, running MATLAB on multi-core processors, GPUs, and clusters. They automatically generate C code from MATLAB algorithms, and they deploy MATLAB components into production environments. MATLAB is the language of technical computing. What can you do with MATLAB?
Welcome to this webinar, Parallel Computing with MATLAB on multi-core desktops and GPUs. My name is Jiro, and I'm an application engineer at MathWorks. Before we begin, I'd like to cover some of the logistics. If you're having any technical difficulties in viewing or hearing the webinar, please use the chat tab to communicate with the webinar host. If you have any technical questions regarding the content, please type them into the Q&A tab, and we'll address them at the end of the session. Now, the main question that we're trying to answer today is, how can we speed up our algorithms in MATLAB? Now, there are plenty of ways that you can do that with just core MATLAB by writing efficient MATLAB code, making use of the matrix capabilities within MATLAB. But today, the focus is going to be how we can achieve this by using additional hardware resources, such as a multi-core, multi-processor computer or graphics processing units, or GPUs. So I'm going to start with a brief introduction, and then we're going to talk about what you can do using your CPU resources, and then what you can do using your GPU resources. Now, the focus today is going to be our parallel computing tools, which is the second bullet, but I do want to mention that MATLAB itself has a lot of built-in multi-threading capabilities. And we call this implicit because these are capabilities that are built in at the core function level. Some of the core mathematical operations, linear algebra and matrix math type of operations are already multi-threaded because we're using multi-threaded libraries. And if you're running on a machine with multiple cores or multiple processors, it will automatically make use of all those resources. Now, since these are all implicit and built into the core functionalities, you don't need to change how you write your code within MATLAB. Okay, so it's very easy to use. You don't really have to think about it. But obviously, not everything in MATLAB is multi-threaded this way, and there may be much bigger problems or bigger simulations that maybe you're running multiple times, and you just run those in parallel. And that's where our parallel computing tools or our explicit tools come into play, and that's the focus of this webinar. So what is parallel computing? So if you imagine this as your current setup, where MATLAB is launched from your operating system, you have your MATLAB desktop, command prompt, and so forth. MATLAB is primarily a standalone, sort of a single user type of environment. Well, what parallel computing is providing you with additional MATLAB resources, additional MATLAB sessions to help you solve your problem collectively. So these individual MATLAB sessions, we'll call them workers throughout this webinar today, but these are essentially MATLABs, but it's kind of running in the background and tied to your main MATLAB session, and they all work together to solve a bigger problem. Now, the main tool that makes this whole thing possible is the parallel computing toolbox. This is just like any other toolbox that you might have, and one of the main goals, main purposes of this parallel computing toolbox is to give you the ability to write parallel applications within MATLAB. But it also allows you to make use of your local hardware resources, whether it be cores, or CPUs, or GPUs. And with a single license of parallel computing toolbox, you can make use of up to 12 workers. Okay, so if you have a machine with 12 cores, you can fully utilize that machine. Now, for this particular workflow, you don't need a separate computer cluster. This is completely a single computer environment. Now, the other use of parallel computing toolbox is the ability to allow you to scale up to a cluster environment if you have a cluster setup. Now, on the cluster side, there will be a product called MATLAB Distributed Computing Server installed to essentially enable all of those machines to become a MATLAB cluster so that you can connect to it using the parallel computing toolbox from your computer. Now, today this webinar is only going to focus on the desktop side, so we won't really touch on the cluster computing side, but we do have a separate webinar that talks about cluster computing. Now, when you're doing parallel computing, not everything is meant to run in parallel. I mean, there are certain classes of problems that are really suitable for parallel computing. And we're going to break it up into largely two different buckets. One that's more about speed. How can you speed up your computation, your computationally intensive problems by making use of cores, CPUs, or GPUs. The other class of problem is something that involves lots of data, large data, okay? And this is more applicable when you're doing cluster computing because you have more computers and more memory resources that you can pull together, and collectively you can deal with very, very large data. And again, we want to focus on the desktop side, so our example is going to be mostly pretty much on the speed side. All right, so let's see what we can do using our CPU resources. Now, our parallel computing toolbox provides you with different ways of doing parallel computing within MATLAB. There are some things that are very easy to use, just a switch or a flag that you turn on and it automatically does parallel computing. And then there are other things that will give you more control, might involve a little bit more programming, but gives you that low-level control of how you parallelize your program. So we're going to take a look at various examples that span this whole spectrum. And I want to start off with one of the easiest ways of doing parallel computing, which is to make use of the functionalities that are already built into the toolboxes. And one of those toolboxes is the optimization toolbox. Now, we're going to take a look at this, a simple example. We're trying to optimize the placement of these circular regions. And you can imagine that this circular region might represent a cell phone tower from looking from the sky, and each tower has this different coverage area. So we start with some random initial placement, and we want to evenly distribute it so that we have this nice coverage with minimal overlap. Okay, so it's a fairly straightforward optimization problem, and we are going to use optimization toolbox to solve this. Okay, so what we have here is a little graphical application that allows me to simulate this by changing the number of towers, the dimensions of this region. We can play around with the tolerance, which affects the optimization routine, and so forth. For now, let me just click on Run and see what it gives me. You can see this animation happening in front of us. And it goes through some iterations, and once it satisfies this tolerance criteria, it finishes. Now in this case, it took about 38, 39 iterations, and this is the final solution. We also have in the code some timing commands to time how long this process took. And you can see here that it displayed in the command window that this optimization routine for this 15 towers took about 8 seconds. Okay, pretty reasonable. But what if we increase our tower? Okay, so I have a different scenario where we have 40 towers. Accordingly, we increase the size of the square region a little bit. And then I'm going to click on Run and see how it's going to do. And we can clearly see that it's a lot slower. It's taking a longer time to go from one iteration to the next. It's understandable because we have more towers that we're trying to optimize, but if we think about it, the way this is solving is by using a gradient-based optimization solver. So what that means is that for each iteration, it's doing many gradient calculations to many finite difference calculations. So obviously, more towers you have, more of those finite difference calculations that it needs to do. Okay, so it's going to take longer. Now the good thing is that each of these finite difference calculations are essentially independent. You can calculate all of them, many of them in parallel. So this is something that's very suitable for parallel computing, and we're going to do that in a little bit. Okay, so we can see that for this 40 towers, it took about almost 50 seconds to solve this. Okay. So what I'm going to do is I'm going to now make use of those workers that I mentioned to run on my computer, my computer that I'm running here, and make use of those cores to help me solve this same optimization problem with additional computational resources. Now the way I would do this is to issue the command matlabparallel and say open. So matlabparallel is a command from the parallel computing toolbox, and I'm telling MATLAB to open additional pools of workers. Now, by default, it's going to open up as many workers as I have physical cores. I'm on a quad-core machine, so it automatically opened up four workers. Let me switch over. Now that I have the workers open, I'm going to go back here, reset to my initial state, and click on Run. And you can clearly see that it's visibly faster. Okay, and that's because all of those finite difference calculations are now being done by the 4 workers that I started. So I'm doing a lot of this computation in parallel. Okay, it's going to finish soon, and we'll take a quick look at how long it took. And it says more than 2 times speed up. Okay, so it's a very significant speed up by making use of these 4 workers. Now, some of you might be wondering, why is it not 4 times faster? Why is it not 12 seconds? Well, it's if you think about it, this is an optimization problem, and not everything in optimization can run in parallel. As I described, the finite difference part, the finite difference calculation part of the optimization routine can run in parallel, but everything else in the optimization process needs to run in serial. So since only part of the algorithm is running in parallel, if you look at the whole time, it's very understandable that it's not a perfect speedup. But we'll see in a second that there are other factors. In general, when you do parallel computing, there's always going to be overhead, whether it be the overhead to break up the problem, overhead to gather the results back, overhead for communication if you're doing cluster computing. So there's always going to be overhead, and that's something you have to really understand and think about when you're doing parallel computing. Okay, so we have a nice speed up, and let's kind of see what the code looks like to make this happen. So on the resource side, I just say MATLAB pool open, and I just open up 4 MATLAB workers on my computers. But if you take a look at the code, okay, and I'm just going to search for fminCon. Okay, so that's the function, the main function that's responsible for doing optimization. This is a command from the optimization toolbox. Now, before I issue this fminCon command, I set some options. Okay, so some of them are just standard optimization options, like what's the tolerance, what kind of algorithm to use. But one of the options that I pass in is use parallel. Okay, and I say use parallel is always, and by doing this, and I pass in this option. You take a look at here. I pass in this option. At runtime, MATLAB goes and runs this fminCon command, and then inside this, there's a place that checks to see if there are any workers running present currently. And if it sees any workers, then it'll run the algorithm in parallel. Okay. If it doesn't see any workers, then it's just going to run normally. And that's why when I first ran this example, I didn't have any workers open, so it was running the serial part of the algorithm. But now that I have workers open, fminCon was making use of those 4 workers to help with the computation. So this was the only difference, only change that I had to do. And since having this option on doesn't affect how it works on a single core scenario, so I can always have this inside here in my code, and everything else is exactly the same as I would have it in any other case. Okay, so this is the one minor change, or the option that I had to pass, and then everything else was taken care of inside this fminCon function, which is from the optimization toolbox. Okay. Now, one other thing is that notice that when I just said open, it just opened up as many workers as I have physical cores, but I can also specify a number after this open parameter and give a different number, and it's going to open up that many workers. So if for some reason I'm doing something else on my computer and I know that I don't want to use all the cores, I can specify MATLAB pool open 2, and it's going to open up 2 workers. Okay, but this number is only limited by that the license, which is 12 workers on a single computer. All right. So this was one of the example where an optimization toolbox function was already parallelized, and all I had to do as a user was to pass in that option or the flag, and everything was taken care of. And in fact, in the optimization toolbox, there are currently 3 functions that behave this way. They all take this use parallel. They're all gradient-based, 3 of the gradient-based solvers from the optimization toolbox. And in fact, there are other functions from other toolboxes as well, as you can see here, such as global optimization, statistics. There's some Simulink-based tools, and so forth. Now, this list is dynamic. We're constantly adding more functionalities to various toolboxes. So we do have a web page that's linked off our parallel computing product page that shows a list of current supported toolboxes with built-in parallel support. Now, one thing to note about these parallel functionalities is that they are all using functions from the parallel computing toolbox. So they're not using any special libraries specific to those toolboxes. They're all just using parallel computing toolbox functions. Okay, so let's take a look at another example where you as a user can use some of these parallel computing toolbox functions. And in fact, if you look at some of the functions in the built-in toolbox functions and open the MATLAB file, you will see some of these parallel computing constructs used inside there. Okay, so we'll look at one of these examples, but it gives you a little bit more control, so it's not completely out of the box and just an option on or off, but it gives you more control on how to break up your problem, but it's still fairly easy to use. So that's why it's here kind of mentioned as high-level programming construct. Okay, so we'll look at part 4, but as we saw in the previous example, you can kind of imagine the types of problems that are suitable for parallel computing is something that involves running similar type of operations over and over again. Similar but independent types of problems. An example of that, or examples, would be parameter sweep studies and Monte Carlo simulations. Both of these are just running similar simulations with different input parameters. Okay, but each of those simulations are completely independent of each other. So instead of running each of these one after the other, you can run them in parallel. And if you have 4 workers, you can essentially cut down on the time that it takes to complete all those 4 different tasks. Okay, so let's take a look at an example, a parameter sweep example, where we're trying to do a parameter sweep of a second order system simulation. So here we have this second order system, and what we're trying to do is we're going to try different combinations of these two parameters, b and k. Okay, and for each parameter combination, we're going to solve this second order ODE. Then from that solution, we're going to pick out a particular value. Specifically, we're going to pick out the peak response or peak value, and we're going to have that for each different combination. So at the end of this study, we'll have this nice matrix of points where I have different stiffnesses or different K values and different B values, and then different peak response on the vertical axis. Okay? So let's take a look at this example here. Now, it takes a little while to run this problem, so I'm just going to go ahead and run for now. And while it's running, let me briefly explain. So we have some initialization where we define the different values of B and K that we want to simulate across. And then this is the bulk of the problem here, where we have the for loop. We're just essentially going through all the different combinations of the problem. We're using ODE45, which is our numerical solver for this ODE system. Oh, here's the output. Yeah, we'll talk about that in a second. And once we solve the system for particular combinations of B and K, we take the maximum value, so this is how we get out the peak response, store it into this variable, and once we have this whole matrix built up, we're just going to visualize it using the surface plot. Okay, so that's the plot that we that just popped up here, values of K, B, and then we have a peak response. Okay. Notice that we have a couple of commands here, tick and talk. So these are commands that allow me to time how long it takes to go from one to the next. So since the for loop is the most computation intensive part of the code, this is where I'm putting my tick and talk. Okay, and we see here that it took about 25 seconds to run this script or run this for loop. Okay, now so a for loop, obviously MATLAB solves it sequentially, so one iteration after another, but we know that this is a completely independent simulation. We're essentially testing different parameter sets, so these are all independent. One result from one iteration does not depend on any other iteration, so I could run all this in parallel. So to instruct MATLAB to run this loop in parallel, I simply convert my for loop to a par for loop, which stands for parallel for loop. Now, if you remember, I still have my 4 workers running You can see here the indicator down here. So by doing part 4, I can go ahead and run it now, because now when MATLAB comes to part 4, MATLAB sees that I have 4 workers open, and then it's going to automatically distribute the iterations to those 4 workers. Okay? So you can see that it's very close to 4 times speed up, because now we have 4 workers working to solve this this single parameter sweep study. Okay, we're also timing just the part that we're trying to parallelize, so we don't have the same type of overhead that we saw in the optimization problem. We have a very good speed up. We still see a little bit of the overhead, but this is just the nature of parallel computing, where when we break up a problem, we have to distribute the data to the different workers, and then we have to gather all the results from the workers to the main MATLAB so that we can do some post-processing. So there's always going to be some overhead when we do parallel computing. Now, notice that what part 4 allows you to do is it allows you to intermix serial part of the code with the parallel part. So everything outside of part 4, this is just regular MATLAB code that's running on this MATLAB session that you're seeing here. Everything inside part 4, these are running in the 4 workers that are essentially running in the background. And then once outside the part 4, the rest of it is now again running on this main MATLAB session. So different MATLAB sessions are running in different parts of the code, and you can easily intermix serial and parallel part of the code. Now, as I've already described, one of the main requirements for this to work is that each iteration has to be independent. Okay. Now MATLAB does have some checks to see whether the loops are independent. So for instance, if I were to introduce a loop dependency, for instance here, okay, so just to make sure that the numbers work out, I'm going to start from 2, and you can see that as soon as I do this, the results for index is dependent on the index -1, so previous iteration. You can see that the MATLAB code analyzer returns a warning that says part 4 would not run because it detected a dependency in the way I used my variable peak values. Okay, so the static code analyzer is constantly running in the background to see if there are any obvious dependencies that it can find, and if it does, it'll flag it with this code analyzer warning. Okay, let's switch over a little bit. So just to summarize, for when you have a for loop that are independent, you can simply convert it to part 4, and if the loops are independent, you can easily have MATLAB automatically distribute it to the workers and run that part of the code in parallel. Okay, but there are some other cases where you may want to run in parallel, but some of these high-level programming constructs may not work. For instance, if you don't have a for loop, so maybe you have a lot of independent but many different types of functions that you're running sequentially, okay, or currently sequentially, but since they're independent, you may want to run them in parallel. Well, since it's not in a for loop, you can't easily use part 4. Okay, so rather than converting that to a for loop first and then using part 4, there are low-level functionalities they can use, functions they can use to introduce parallelism in that type of code, and those are concepts called jobs and tasks, where you can explicitly state what your tasks, independent tasks are, and then have them run in parallel. And for that, you can specify different functions as different tasks. Because of in the interest of time, I won't run the example, but I will show you the code briefly, and just to show you what those jobs and tasks may look like. Okay, so here's an example, similar problem, the parameter sweep example, but in this case, instead of having a for loop, let's say my goal is to compare the results from different types of numerical solvers. So I have 4 separate functions which are all independent, and they all take in some type of input arguments. And then I'm just testing out different types of solvers. So inside here I just have different ODE solvers. But instead of running them one after the other, which this is how I would do it normally, I can make use of jobs and tasks to make that happen in parallel. And for that, they're a little bit more programming on your part, because everything is now under your control, so you have to kind of specify every little step of the way. But there are mainly 4 different steps. One is the first one is to create your job. And a job is essentially like your problem that you're defining. And for your job, you'll specify any user-defined functions that you might have. So these are all of my .m files that I have. And then I create as many tasks as I have using the create tasks function. And for that, I can specify different function files, or I can specify even same functions, but maybe different input arguments. So I just create one task after another. Okay. So up to this point, I'm simply defining my problem. Okay. I'm not executing any of them. So this happens fairly quickly. And once I define everything, I go ahead and submit it. And at this point, this problem gets packaged and then sent to my workers in the background. Well, the nice thing about this process is that it completely offloads my computation from my MATLAB session. So it's going to be running in the background, and it frees up my MATLAB session, this main MATLAB session, which I can use for other computation. Okay. Now, once the problem or the job is completed, then I need to now bring the data back. So the last step is to say fetch outputs, and that's going to bring the data back from all the different tasks that were computed. Okay, so that's the low-level use of doing parallel computing, where you explicitly state which part of the problem you want to break it up and how you want to break it up. Now, some of these things I won't be touching on today, because these are more applicable to cluster computing. But just to kind of give you a brief description, explanation. So LabSend. So these are some of one of the commands that allow me to have the different workers talk to each other. So let's say if I want to have one worker send data to another worker, and then another worker will send some other results to a different worker, you can use these MPI commands, message passing interface commands, to send data and receive data. You can also tell different workers to stop and wait for one of the workers to finish. So these are very low-level inter-worker communication commands. Batch is kind of similar to what we saw with the jobs and tasks. This is a way of just taking a script or function and completely offloading to the workers. Okay, so it's a very convenient version of jobs and tasks, but we can take that same parameter sweep example, that par4 example, and pass that script through this batch command, and it's just going to offload it to the workers. And once it's offloaded, my main MATLAB session is free, so I can do other stuff while it's running in the background. Okay, distributed. This is a way of this is more on the large data side. How the ability to take your variable and then distribute it across different workers, so that all the workers are storing portions of your array, and but then collectively they can work together to solve on this big array. Okay, so we're going to switch gears a little bit, and we're going to talk about graphics processing units. So graphics processing units, I think most of you are aware of. These are the graphics cards that are on your computer. Almost all computers have some sort of graphics card, and as the name suggests, it's used for graphics rendering, 3D rendering. Some high-end gaming machines have very powerful graphics cards to help with the 3D rendering. But more recently, people started to use graphics cards for scientific computing. Now, GPUs are very different from CPUs. Where CPUs, you have dual core, quad core, 8 cores, and sort of single-digit cores. But GPUs, they have hundreds of these cores per card. Okay, but the units of these cores they have different uses. They're really useful and very powerful for doing a lot of number crunching, doing matrix math, and a lot of adding and subtracting, doing some operations on numbers. So that's what they're good for. So they have certain types of problems that they're suitable for. Okay, so and that really defines what types of problems are really suitable for GPU computing and what are good for CPU. So with Parallel Computing Toolbox, we can work with a particular type of GPUs by NVIDIA, and we have this requirement that the supported cards require the compute capability of 1.3 or greater. So these include most of the modern cards by NVIDIA, but includes the NVIDIA Tesla 1000 and 2000 series. Now, because architecturally they're very different, GPUs and CPUs, the way you use them are also very different as well. As we saw up to this point, for CPUs, the way you would use it is to make use of workers. Okay, so we would start up, use the MATLAB pool command to open up MATLAB workers, and the workers are essentially additional MATLAB processes that would make use of the cores that you provide. On the GPU, you don't really start up MATLAB processes. You can't. They're not really meant to have processes running, but they're great at taking instructions and commands. And what you do is you make use of the memory that's on board the GPUs. So there's a command that will allow you to push data onto the GPUs, and then you issue threads of instructions. For instance, you have your data there and say multiply by 2 or take a sign of this matrix. And those instructions are done in parallel by making use of all those units on the GPU. Okay? So just like on the CPU side, there are various ways of making use of GPUs with the Parallel Computing Toolbox. So we'll take a look at one example that uses the easiest interface called the GPU array. Now we're going to look at solving a second-order wave equation using spectral methods. Now, spectral methods involve a lot of FFTs and inverse FFTs, and those are great. Those type of operations are perfect for GPUs. So this is a great example to show you the power of GPU computing. Okay. So if we take a look at this graphical application that we have, this allows us to test solving this problem using the CPU and GPU. We can also change the grid size. We can also change the number of iterations to go. So let's start with the simple case. We're going to test the CPU for a small grid size. Okay, and we can see here through this animation that it's solving the second-order wave equation. The top animation shows the actual solution, and then the bottom graph shows the delta between two time steps. Okay, so for this grid size, the delta really isn't required. You can just see the actual solution, but we'll see in a second that the delta becomes a little bit more important for a larger problem size. But it took about 15 and a half seconds. Okay, so that's pretty reasonable. Okay, but let's test out a really large problem, or significantly larger problem. So 512 by 512. And since I already know that it takes longer, I'm only going to go up to 200 time steps. Okay. Now we can see that it's going much slower. Okay. Now for this problem, when you increase the grid size, obviously you have more grid points, so more points to compute. So obviously that makes it more complex. But the other thing that happens is that when you increase the grid size, the time step becomes shorter in order to converge to solution. So every little iteration only goes by a very small time step. So you can't really see any change in the main plot, but you can see that there is some change by looking at this bottom plot, but clearly from the time scale, from the scale 10⁻⁵, the change is very small. Okay. All right. So for 200 iterations, it took about 45 seconds. Okay. Now if you switch over to GPU for the same problem, we can see that it's significantly faster. Okay, so almost 6 times faster on a GPU than a CPU. So you see that for this problem, for a certain grid size, GPU is much faster than a CPU. So we actually did a benchmark, a full benchmark on this study using various grid sizes, and what we found was that as you increase the grid size, the GPU speed up increased. Okay, and in fact, we were using a slightly different machine for both CPU and GPU, so the speed up value is slightly different from what we saw just now. But we can see that the largest size that we tested, the speed up on the GPU was about 7.5 times faster than CPU. Okay, but the other thing that we see here is that for a small grid size, CPU was actually faster. Okay, the reason for that is because for small problems, it's actually spending more time transferring data back and forth between the GPU and the CPU than spending time actually doing the computation on the GPU. So the overhead of data transfer dominated, and that's why you see a better performance on the CPU side. But as you increase the grid size, you are sending more data, but you are sending much more significant time doing the computation on the GPU, so the overhead isn't as big of a deal. So you see a better performance on the GPU side. Okay, so we saw some performance information. So now let's take a look at what the code looks like. Okay, what does it take to run your code on the GPU? So what we have here is two examples, two versions of the code, one for the CPU and one for the GPU. And I'm just going to open it up using the file comparison tool to see what those differences are. Okay, so with this tool, what you can do is you can put two files side by side, and with the color coding, you can see the differences. So all the places where you don't see any colors, that means that the two files are identical, and wherever you see colors, that they're different. Okay, so obviously the file name is different, or the function name is different. We scroll down, and here's the first difference in the code. So we're using this function GPU array, and this is the function that pushes the data onto the GPU, that GPU onboard device memory that I was showing you in one of the slides. So here I have this X value that was defined on the CPU side, okay, and then by issuing the GPU array, now this new X is now sitting on the GPU. Once I have the data on the GPU, any operation that I do on it happens on the GPU. So this transpose is happening on the GPU. So the GPU is doing the transpose, and then it creates another data on the GPU. So now, after this line, I have X and Y both on the GPU. And I can keep going here. Here's another command, mesh grid is done on the GPU and creates two more variables. And one by one, it creates more and more data on the GPU. Okay. Here are a few more lines that I need to explicitly transfer over to the GPU. So I have 3 more calls to GPU array. And then a lot of other commands that just implicitly happens on the GPU. And then here's the core part of the algorithm. This is where the algorithm starts. The while loop is going through one iteration after another. And notice that pretty much everything is identical. So you don't see any color differences here. So things like indexing, FFT, real, transpose, multiply, IFFT, these are all supported functions to work on data that's on the GPU. Okay, so the difference between the two files here, everything here is running on the CPU, everything here is running on the GPU, because the data, these data are already sitting on the GPU side. Now occasionally, if you want to bring the data back to the CPU side, there's a counterpart to the GPU array command called gather. So gather will take a GPU data and bring it back to the CPU side. So maybe you want to call commands that are not supported in the GPU, or maybe you want to save it out to a file. You would use the gather command to bring it back. Okay, and then one last gather at the end. So that's the only change between the two code, and then pretty much all the algorithm that we have here is because we're using all the supported functions for GPU data, GPU array. I didn't have to do any change to the code. Let's take a quick look at the documentation to see the list of the supported function for GPU array data. Okay, so if you go down to Parallel Computing Toolbox, User's Guide, and then there's a section on GPU array or GPU computing, and then click on GPU array. And this page talks about everything about GPU array and how to use it. You can also create data directly onto the GPU array. So ones, zeros, ran. These are all commands that run directly on the GPU to create data. And then if we scroll all the way down, we see this list of supported function for GPU array data. Okay, as you might expect, because of the nature of GPUs, they're great at doing these element-wise numerical operations. So most of these are mathematical element-wise operations. There are some other high-level functions, some signal processing type of functions like filter, FFT, inverse FFT, and so forth. But you can see that we have this huge subset of MATLAB commands that are out of the box supported for GPU data. This list is also fairly dynamic, so every release we're adding more and more functionality. So I would encourage you to take a look at this every time you upgrade to a new version of Parallel Computing Toolbox. Okay, so that was a very simple example using GPU array. It's really meant for a very ease of use, but we do have a more sophisticated way of targeting GPUs and to give you more control of what you're trying to do on the GPU. So while GPU arrays, we have this built-in functions that allow you to kind of send data onto the GPU and then apply functions. We also have abilities to combine some of those element-wise operations together and then apply them all at once to data that's on the GPU. So that gives you a more efficient way of executing commands on the GPU. And finally, if for those of you who are familiar with CUDA, to program specifically for NVIDIA GPU cards, if you have those CUDA code, we have the ability to take that and then compile it and run it directly from within MATLAB using the Parallel Computing Toolbox. Now this was a fairly short overview of GPU computing, but if you want to know more about it, we do have a dedicated webinar on GPU. So I encourage you to go to our MathWorks website and search for GPU computing with MATLAB recorded webinar, and you can take a look at that. And that webinar talks about all these just 3 different methods, and you can see 3 different examples that touch on the different techniques. We saw one example, something that involves spectral methods and FFTs and IFFT, and we saw that that was a great problem for solving on GPU. But there are some things to consider when you're thinking about whether your problem is right for the GPU. One, because of the nature of GPUs, you really want to be doing something that's massively parallel. So something that you can do element-wise, something that you can just put on a matrix and then just break it up into different chunks and then run similar operations on each of the elements. Okay, so that's making use of the architecture of GPU. We also want something that's very computationally intensive. But in fact, this is, as we saw, in relative to sort of the data transfer. So ultimately, you want to be spending more time doing the computation on the GPU than transferring data back and forth. Okay, so that's very important. And finally, if you are using things like GPU array or the element-wise operation ArrayFun, you want to be make sure that the functions that you're running are supported on the GPU. And we saw in the documentation where you can find a list of those functions. Currently, we do have one toolbox that has some built-in GPU support, and that's the communication system toolbox. And they have a number of handful of functions that automatically target the GPU when you use those functions. All right, so let's recap. We looked at different technologies to speed up your computation. We looked at MATLAB Pool and MATLAB Workers to help you speed up your for loops. And then we looked at user-defined tasks where you can explicitly break up problems using jobs and tasks. And then we looked at an example that targeted the GPU using the GPU array function. All right, so in summary, we talked about various technologies that allow you to speed up your computation using hardware resources on your computer. Specifically, we focused on your local resources. Again, the other half of the parallel computing story is that you can scale up to a cluster of grids or clouds, but that wasn't the focus of this webinar. We do have a separate webinar that will kind of go into the cluster computing. But all this will allow you to make use of any CPU or GPU hardware that you might have available to you around your machine. Okay, if you want more information, including links to this webinar, links to other examples, links to different webinars that's related to this topic, please go to the product page for Parallel Computing Toolbox, or this link here, and you can get a lot of information that may be helpful for people who are getting into parallel computing. All right, so at this point, we're going to take a short break, and when we come back, we'll address as many questions as we can in the remaining time. So again, if you have any questions, please go ahead and fill them into the Q&A tab. So that's the tab with the question mark, and we'll come back and address them. So we'll talk to you soon. Thank you.
Computer has in order to do the execution of multiple processors? And the answer is no. If you want to go ahead and open up a pool of workers with MATLAB, all you need to do is just run MATLAB pool open, and you don't need to specify the number of actual workers. And MATLAB will find how many workers are on your computer, how many cores are on your computer, and then go ahead and execute with that. Another question here was, will MATLAB support ATI GPUs? Currently, MATLAB only supports NVIDIA, so that's the current situation. Okay, so here's another question. The question is, let's see, in the case that the optimization algorithm is not gradient-based, would this cause any issues to the parallel scheme? So typically, there's a use parallel flag for a lot of the optimization routines, such as fmin-con, or if you're doing things like global search or multi-start using the global optimization toolbox. But if there is not a use parallel flag, then you may not be able to go about and parallelize the scheme. But you can always go ahead and build out your own solvers if you need to in order to do that. Okay, here's another question. Let's see. So another question is, can we download the scripts shown on the webinar? Yes, so all all of these examples here will be made available to you within the week, and you should be able to download them through MathWorks. Okay, let's see. Looking for another question. Let's see. Okay, here's another question. How can I write data to a disk when doing GPU computing? So the answer with that is that you can't directly write to a disk when you're doing GPU computing using the GPU array function. You have to first gather it to your CPU, and then once it's on your CPU, you can go ahead and write it to disk. Let's see. Okay. Another question here is, how do I set my parallel environment to a cluster? And the answer to that is that on your MATLAB tool strip, there's a little button that says parallel on it. If you click on that, you can go ahead and specify a different parallel working environment. By default, it's set to your local environment, but you can go ahead and specify a cluster or a grid if you have access to one. Okay. Let's see. Looking for some other questions. Okay. Is parallel running in embedded MATLAB blocks in Simulink? So there is a nice case study online that I've seen for doing the parallel sweep that you saw today, but using a rapid accelerator target with Simulink. And the way that works is if you open up a pool of MATLAB workers and then you run par4 in MATLAB, then you can go ahead and use par4 from Simulink inside of MATLAB. So you have to specify that. By default, it's not running. Okay. Let's see. So the question is, how do I gather the data from the GPU to the CPU? So the answer to that question is there's a gather command that you just basically pass in the array into the gather function, and then it'll put the information from the GPU back on the CPU. Okay. Let's see. Okay, here's another question. Are all optimization routines capable of using parallel computing? What about LSQ non-lin, for example? So not all of the optimization routines in the parallel computing toolbox are capable of using the parallel computing toolbox with just a flag. For example, using the use parallel. But you know, some of the most commonly ones like fmin_con can be used with the use parallel flag. You can always, of course, go ahead and if you have a specific optimization routine that's specific for your particular application, you can go about doing low-level parallel loops such as lab send or lab receive instead of relying on the use parallel, but that will, of course, require a little bit more code. Okay. Let's see. Okay. Is there a tool that shows MATLAB's dynamic core usage as we run our applications? So there's no tool that shows you how much each core is being used. That's kind of done partially by the operating system sweeping between the different workers and doing load balancing there. So there's no tool to kind of specify, you know, how much one particular worker is being utilized over another and control that. Okay, so it looks like there's a few more questions here, but we're kind of coming to the end of the hour here, so that's going to be all the time we have for today. For those of you I didn't get a chance to respond to, I'll go ahead and follow up with an email. Also, there are demo files on the Exchange that I will make sure to include in a link and send these demos out to you guys in a follow-up email, and you should expect to receive that within about a week. So thanks for listening, and have a nice day.